Welcome, everyone. I'm excited to kick off our presentation today on chemical equations and reactions. This is the first slide, and it's our cover slide. We'll be exploring the fascinating world of chemistry, how substances interact, change, and form new compounds. Over the next few slides, we'll cover the basics of chemical equations, how to interpret them, and what they tell us about reactions. So let's get started and dive into this intriguing topic. Let's begin by understanding what chemical reactions are. Essentially, a chemical reaction is a process where substances interact to form new substances with different properties. This is the foundation of everything we'll explore today. Moving forward, we'll look at how we identify these reactions, which is crucial for understanding what's happening at the molecular level. Once we can identify a reaction, we can make our chemical equations more informative by including details like conditions and states. As we dive deeper, we'll examine various types of chemical reactions, including displacement reactions, neutralization reactions, and more. These categories help us organize and predict how substances will behave. We'll also explore specific concepts like oxidation and reduction reactions, which are essential for understanding many processes, from corrosion to biological systems. Additionally, we'll discuss the importance of balanced chemical equations. They ensure our reactions obey the law of conservation of mass. We'll see how to write these equations accurately. We'll also cover exothermic and endothermic reactions, which tell us whether energy is released or absorbed during a reaction. Furthermore, we'll look at corrosion and rancidity, two common examples of chemical changes that affect our daily lives. And finally, we'll bring everything together in the conclusion, summarizing the key points and their relevance to understanding chemical behavior in real-world scenarios. Let's take a closer look at this example of a chemical reaction. On the left, we have the reactants, which are the starting substances. In this case, it's 2 atoms of sodium, represented as 2 Na-S, and 2 molecules of water, shown as 2H2O. When these react, they undergo a chemical change. On the right side, we see the products formed from this reaction. The products are sodium hydroxide, which is shown as NaOH in aqueous form, and hydrogen gas, H2, which is released as a gas. This example highlights the fundamental idea that in a chemical reaction, reactants are transformed into products with different properties. Understanding this process is key to grasping how chemical reactions drive many processes around us. It also emphasizes how the substances we start with can change into entirely new substances through chemical reactions. Now, let's talk about some key signs that tell us a chemical reaction is happening. One of these signs is the evolution of gas. When a gas is produced, you might see bubbles forming or notice a new smell. Another important indicator is the formation of a precipitate, which is a solid that appears when 2 liquids react together. Changes in color are also common. For example, a solution might turn from clear to cloudy or change to a different shade altogether. Temperature change is another clue. Reactions can either release heat, making things warmer, or absorb heat, causing cooling. Lastly, a change in state, such as a solid turning into a liquid or a liquid turning into gas, can also signal a chemical reaction. Recognizing these signs helps us understand when a chemical change is taking place, which is crucial in studying chemistry and understanding how substances interact. Now, let's look at a common example of a chemical reaction. 2H2 plus O2 yields 2H2O. This is a simple yet powerful illustration of how elements combine to form compounds. When we write this symbolically, it's representing the process in a concise, standardized way. In fact, when hydrogen and oxygen combine, water is formed, which is essential for life. This symbolic representation helps chemists understand and communicate reactions clearly and efficiently. Remember, a chemical equation isn't just random. It's a precise way to show what's happening during a reaction. There are 3 main ways to write these equations: the word equation, the symbolic or chemical formula, and the balanced chemical equation. Throughout this presentation, keep in mind that understanding these representations is fundamental to grasping how chemical reactions work and how they connect to the broader themes of chemistry and scientific application. A balanced chemical equation is all about ensuring that the law of conservation of mass is maintained. In other words, the total number of atoms of each element must be the same on both sides of the equation. This means that when reactants turn into products, no atoms are lost or gained. They are simply rearranged. Achieving this balance is crucial because it reflects the actual chemical process happening at the atomic level. Throughout this presentation, we've seen how balancing equations helps us understand the precise relationships between reactants and products, making our chemical calculations accurate. So always remember, a balanced equation is the foundation for understanding chemical reactions correctly. On this slide, we're exploring how to make chemical equations more informative. When writing these equations, we include symbols to show the physical states of the reactants and products. For example, S indicates a solid, L a liquid, AC means the substance is in aqueous solution, and G stands for gas. We can also use arrows to show the formation of precipitates and gases. A downward arrow, called a down arrow, indicates a precipitate forming, while an upward arrow, up arrow, shows that a gas is evolved. For instance, in the reaction shown here, sodium reacts with water to produce sodium hydroxide in aqueous solution and hydrogen gas, which is represented by the arrow pointing upwards. By including these symbols, we make the chemical equation more detailed and easier to understand, providing clearer insight into what's happening during the reaction. This helps us communicate the process more effectively and accurately. Now, let's explore some of the main types of chemical reactions that we encounter. First, we have exothermic and endothermic reactions. Exothermic reactions release energy, usually in the form of heat, making the surroundings warmer. In contrast, endothermic reactions absorb energy, often cooling the environment. Recognizing these helps us understand energy flow during reactions. Next, there's the decomposition reaction. This is where a single compound breaks down into simpler substances. Think of it as a complex molecule splitting apart into its components. It's often triggered by heat, light, or catalysts. Then we have oxidation and reduction, which are closely linked. Oxidation involves a substance losing electrons, while reduction involves gaining electrons. These processes often happen together, such as in rusting or cellular respiration, and are fundamental to many biological and chemical systems. Moving on, we come to the combination reaction. This is where two or more substances combine to form a new compound. It's like building something new from smaller pieces, and these reactions are common in synthesizing materials. Finally, there's the displacement reaction. Here, one element replaces another in a compound. Think of it as a more reactive element taking the place of a less reactive one. These reactions are important in processes like metal extraction. These different types of reactions show how versatile and dynamic chemical processes are. Recognizing these helps us understand the overall theme of how substances interact and transform, which is central to mastering chemistry. Let's take a closer look at this reaction. CaOS plus H2O, which produces CaO2 AC and releases heat. Calcium oxide or quicklime reacts very vigorously with water. This reaction forms calcium hydroxide, also known as slaked lime, and it's important to note that it's highly exothermic. That means a lot of heat is generated during the process, so it can get quite hot quickly. Now, to connect this to our broader theme, this is a classic example of a chemical reaction where reactants come together to form a single product, in this case, calcium hydroxide. This type of reaction is called a combination or synthesis reaction. It's a fundamental concept because many reactions in chemistry involve multiple reactants combining to make one new compound. Understanding these reactions helps us see how substances interact energetically, which is crucial in practical applications like construction, where lime is used in mortar and plaster. So, recognizing the energetic nature of such reactions also highlights the importance of safety when handling reactive substances like calcium oxide. Now, let's look at some specific examples of decomposition reactions. First, consider the reaction. 2NaCl transforming into 2Na and Cl2. This is a classic example where light energy is used to break down a compound, and we call this process photolysis. It's important because it shows how energy sources like light can facilitate chemical changes. Next, we have the example of water, 2H2O breaking down into 2H2 and O2. This process uses electrical energy, and it's known as electrolysis. It's a key method in industry for producing hydrogen and oxygen, and it highlights how electricity can be harnessed to decompose molecules. Then there's thermal decomposition, where heat is the driving force. For instance, calcium carbonate, CaCO3, when heated, decomposes into calcium oxide, CaO, and carbon dioxide, CO2. This demonstrates how heat energy can cause certain compounds to break apart. Finally, I want to emphasize the general idea of decomposition reactions. Essentially, a single reactant breaks down into two or more products. The general form looks like Ob turning into A+. B. Recognizing these reactions helps us understand many natural and industrial processes where complex molecules are broken down into simpler substances. Let's take a closer look at some examples of chemical reactions. For instance, the combustion of carbon dioxide and water can be represented as 6CO2 plus 12H2O, yielding C6H12O6, 6O2, and 6H2O. This helps us understand how molecules interact during reactions. Now, moving on to the key concept of endothermic reactions. These are reactions that absorb heat or energy from their surroundings. A common example is the reaction of methane with oxygen. CH4 plus 2O2 produces carbon dioxide, water, and importantly, heat. On the flip side, we have exothermic reactions. These are reactions that release heat as they proceed. When substances react and heat is given off, it's called an exothermic reaction. The formation of products often involves the release of energy, which can be observed as heat. In summary, the main difference is that endothermic reactions absorb energy, while exothermic reactions release energy. Recognizing whether a reaction is exothermic or endothermic helps us understand energy flow in chemical processes, which ties into the overall theme of energy changes during chemical reactions. Now let's look at this example. Na2SO4 plus BaCl2 produces BaSO4 and 2NaCl. This illustrates a double displacement reaction, which is also known as a precipitate reaction. In these reactions, two different ions or groups of atoms in the reactants are swapped, leading to the formation of new compounds. It's important to remember that double displacement reactions often result in the formation of a precipitate, a solid that forms out of solution. Moving on to the next example, zinc reacts with copper sulfate to give zinc sulfate and copper. Here, a single element, zinc, reacts with a compound, copper sulfate, and replaces the copper in that compound. This brings us to single displacement reactions, where one element displaces another within a compound. The key point here is reactivity. When a more reactive element displaces a less reactive one, the reaction occurs smoothly. So, in summary, displacement reactions are all about the movement of elements within compounds, driven by reactivity differences, and they play a crucial role in many chemical processes. Let's look at this example. NaOH plus H2SO4 gives us NaSO4 plus H2O. This illustrates a typical neutralization reaction, where an acid reacts with a base. When they combine, they produce a salt and water. This type of reaction is fundamental because it helps us understand how acids and bases interact chemically. Throughout this presentation, we've seen how these reactions play a vital role in various chemical processes. Recognizing a neutralization reaction is key to understanding many practical applications, from industrial processes to everyday chemistry. Let's take a closer look at oxidation and reduction reactions. These are fundamental chemical processes that involve the transfer of electrons and changes in oxidation states. On this slide, you'll see a table that highlights the key types of oxidation and reduction. First, oxidation typically involves the addition of oxygen to a substance, which often results in an increase in its oxidation state. For example, when copper reacts with oxygen, forming copper oxide, copper is oxidized. Conversely, reduction involves the removal of oxygen or the addition of hydrogen. Take potassium chlorate decomposing into potassium chloride and oxygen as an example. Here, oxygen is being reduced because it's being released. Another important concept is the removal of hydrogen, which also signifies oxidation. In the reaction between hydrogen sulfide and oxygen, sulfur is released and water is formed. Conversely, the addition of hydrogen, like in the reaction where sodium reacts with hydrogen gas to form sodium hydride, signifies reduction. Finally, let's discuss electron transfer, which is central to these reactions. When a substance loses electrons, it's oxidized, like zinc losing electrons to become zinc ions. Conversely, gaining electrons means reduction, zinc ions gaining electrons to revert back to metallic zinc. Connecting this to the overall theme, understanding these fundamental reactions helps us grasp how energy is transferred in chemical processes, which is essential in fields ranging from industrial chemistry to biological systems. Now, let's talk about reactions where oxidation and reduction happen at the same time. These are called redox reactions. They're quite important because they involve a transfer of electrons between substances, which is fundamental to many chemical processes. Next, we have the concept of a reducing agent. This is the substance that causes another substance to be reduced, meaning it donates electrons. Think of it as the helper that gives away electrons to another substance. For example, in the reaction CuO plus H2 producing Cu and H2O, the hydrogen acts as the reducing agent because it provides electrons to reduce copper oxide to copper. On the flip side, we have the oxidizing agent. This is the substance that causes oxidation in another substance by accepting electrons. It's like the electron receiver in the reaction. Understanding these agents is crucial because they drive the whole redox process. They tell us who is donating electrons and who is accepting them, which helps us understand how different reactions occur and how energy is transferred in chemical systems. Connecting this to the overall theme, recognizing oxidizing and reducing agents helps us predict reaction outcomes and design processes in fields like energy production, metallurgy, and even biological systems. Now, let's talk about some methods to prevent corrosion, which is a major concern for metals exposed to harsh environments. You might have heard of techniques like electroplating, galvanizing, and painting. These are all effective ways to protect metal surfaces. Electroplating involves coating the metal with a thin layer of another metal using electrical current, which helps prevent the underlying metal from reacting with air and water. Galvanizing, on the other hand, is when we coat iron or steel with a layer of zinc. Zinc acts as a sacrificial metal, meaning it corrodes first, protecting the main metal below. Painting creates a barrier between the metal and the environment, stopping air, water, and chemicals from coming into contact with the metal's surface. So, in summary, these methods are essential in industries and everyday life to extend the lifespan of metal objects and structures. Remember, corrosion is a natural process where the metal's surface is slowly eaten away due to reactions with air, water, and chemicals. The specific corrosion of iron, which results in rust, is a common example we see often. By applying these protective techniques, we can significantly reduce the damage caused by corrosion and keep our metals looking and functioning their best for longer. Let's talk about some effective methods to prevent rancidity in our foods. First, it's important to avoid keeping cooked food in direct sunlight because exposure to sunlight accelerates oxidation, which leads to rancidity. Instead, always store cooked foods in a cool, shaded place. Refrigerating food at low temperatures is another key approach. Cold slows down the oxidation process, helping to keep food fresh for longer. Adding antioxidants is also a common method. Substances like butylated hydroxyanisole and butylated hydroxytoluene are used to prevent the fats and oils in food from oxidizing too quickly. These antioxidants effectively delay the development of rancidity. Another technique is packing food in packets containing nitrogen. Nitrogen displaces oxygen in the packaging, reducing the chances of oxidation. This helps maintain the quality and extends the shelf life of perishable items. Lastly, keeping food in airtight containers is crucial. When food is sealed tightly, it minimizes exposure to oxygen, slowing down the oxidation process and preventing rancidity. Overall, these methods, controlling exposure to sunlight, refrigeration, antioxidants, nitrogen packing, and airtight storage, are all about protecting our food from the slow oxidation of fats and oils, which causes that undesirable change in smell and taste we associate with rancidity. I hope you all understood. So, as we wrap up, I want to emphasize the key points we've discussed today. First, we looked at the main concepts and how they connect to the overall theme of our presentation. It's important to remember the significance of each point and how they build on each other. Throughout, I aim to make these ideas clear and relatable so you can see their practical value. Ultimately, the goal was to give you a solid understanding and tools you can apply moving forward. Thank you for your attention, and I appreciate your engagement throughout this session.